more formal statement of a stabilization problem. The car example is just an example. So in general, we give a plant. Right? We need to select a sensor and actuator and design a controller so that the closed loop system, the whole system works properly, has a good stability. Of course, what do you mean by good stability? Intuitively, it's just like it works in a smooth way, roughly, in a desirable way. Okay. All these things will be further formalized using mathematical language later on. And we're going to solve this problem. First in a mathematical way, then you probably go into a real system and try to apply to a real system. Stabilization is the first problem. Now the second problem, regulation. Now again, we take this car driving as an example. But now suppose that we're driving in a hilly road, up and down, and we need to follow the speed kind of limit. We cannot drive too fast, we cannot drive too slowly, right? So we have a desirable speed. Suppose that the speed is a kind of constant, say 100 kilometers per hour. The road is like up and down. So, what do we need to do? Again, this car is a plant. The human driver is the controller. The speed instruction is external instruction. We have external command. So the external command say, okay, at this segment you drive 100 kilometers per hour. At that segment you drive like 80 kilometers per hour. So that actually this command can change with time. Typically it changes like a piecewise constant way. Huh? Then you say, okay, I drive the car, I wish to keep my speed, but you have a wind gust, you have like a hilly road up and down, or these kind of things. How do you do it? In a good way. So you first of all, you need to actually try to keep the speed. Actually, you also need to reject the disturbance. Yeah, the wind gust is possible disturbance. And this hilly road is also considered as a disturbance. So you want to reduce the effect of this disturbance. You want to keep your speed as a constant. So how to do it? That's what we worry about in this situation, in the situation of regulation. Again, you can feel open loop control is not going to work well. Right? So you cannot set your pedal position or movement in advance. Right? So you have to make adjustment according to the actual the speed. You probably have to somehow compare your actual speed with desirable speed, and look at the speed error, using that error to make adjustment. So again, you see the advantage of closed loop control over the open loop control. So in this case, actually, you may say, okay, what's the difference between regulation and the stabilization? And the main difference is that now we have external command. So control system in all of our applications is supposed to follow an external command. This command again is something you cannot control. Right? So that's why in regulation you have this external command. In the stabilization issue problem, you don't have this external command. So that's a big difference. Now let's look at the block diagram of a regulation control system. Again, you have plant, you have actuator and sensor, you have a controller. But now, see, the difference is that now we have an external command. So external command is called a reference signal. We call it reference signal. The controller takes both the reference signal and the actual, the measurement. Yeah, so basically the outcome of the plant. And make some kind of comparison. So these two pieces of information. So this R is one piece of information control receives. And R in general changes with time. Y, okay, the measured signal, feedback signal, so second piece of information, and put it in and generate control signal. So probably that's the only difference here. See? Only difference if you compare regulation and stabilization. So this difference actually is kind of a crucial. So this difference makes the controller like more complicated because the controller has to take two pieces of information and send out one control signal. Right? So you have two pieces of information here. This controller, if you look at the information flow, information flow goes from here to there, also goes from here to there. So you have two parts here. This controller is called a 2 degree of freedom controller because you have one part, you have two parts of the process. So later on you probably can appreciate this word 2 degree of freedom controller. 2DOF controller. You will appreciate this word further. So regulation problem, if we state it in a formal way, again look at this block diagram. Given a plant, select a sensor and an actuator, and design a controller. So that the output of the closed loop system track the reference signal. So the output Z tracks this R and eliminate the effect of disturbances. Eliminate the effect of the speed. So tracking is probably the more important thing. So we're going to look at this tracking. You have something coming, and this guy has to follow this guy. So that's an additional feature in regulation problem compared to the previous stabilization problem. Okay, so let's again recap what we have talked about so far. We have two problems, stabilization and regulation. We're going to study both problems and look at solutions. We're going to do experiment on those problems. We're going to have experiment on stabilization problem and regulation problem. So in stabilization problem, you don't have a reference signal. You just want to make things work in a kind of natural way, natural, nice way. regulation problem, you want to make the system to follow some kind of external command. Yeah. So sometimes you also have different features in the disturbances, right? So we can look at that later. So the most important difference in the controller due to the presence of a reference signal is that in the first problem, sterilization problem, the controller only takes the feedback signal. In the regulation problem, the controller takes both signals, reference signal and the feedback signal. So that's why this controller is called two-dimensional feedback controller. In order to solve a regulation problem, you need to first solve stabilization problem. So regulation problem can be considered as a further step of stabilization problem. Without stabilization, you cannot do regulation well. You can see at least in the regulation problem, you set the reference signal to be 0, right? Or the command is 0. Then that's essentially a stabilization problem. So that means even without the reference signal, the regulation system has to work well. So that's why you need stabilization. I think you can have a rough feeling of those things. Okay. Yeah, we have a look at 2 examples. 2 real-life examples to capture some kind of essential ideas in control. So let's now look at some very basic concepts we need to deal with, we need to actually use in study control. Before we talk about the control system, or even a system, we need to know what is a signal. A signal is a time function. So from real line, y-axis. This y-axis is time. To a real value. So real value, that's a signal. So very often you can draw a signal by like a waveform. Right? So that's what we often do. So this is the time axis. So we have, say origin is here, that's time equal to 0. The vertical axis is whatever signal. Let's call it xt. So the signal is just like a waveform.